tonight we are graced with an RF expert, Dr. Edison Fong, and he has inside of this is a Jpole, and he has come up with a very efficient method and model of antenna. A number of us in the club have them. Yep, there you go. There's the roll-up Jpole. Thank you. Anyhow, he's going to take us on a tour of this and show us what we're doing. And if you all remember, Greg and I are hoping that over the next couple of weeks, we're going to review a bunch of different antennas and stuff, and that hopefully we will have built some of our own antennas for field day this year. So, Dr. Fong, take her away.
Thank you very much, Justin. Tonight we're going to talk about the way we did this dual band antenna. That was almost 20 years ago when we came up with this problem. But this is a pretty well understood technique, pretty well accepted now in the amateur radio community. We originally published it in 2003, back in February. So that's almost 20 years ago. And we've done other articles on it. A lot of people have talked about it. So it's in the ARRL Classics Antenna Handbook now. And they have a few working models there. We sent them. So it works. It's a design that really works. And I have to say, whenever you hear designs that people go, try this, and this gives 6 dB, this gives 50 dB and all that. My general conclusion is if you don't see it, and if it's a good idea, the ARRL would have caught on to it and it would be published. If you don't see it published, it's very skeptical of believing whatever the game is. An example is the Slim Jim antenna. So, but if you see it in the ARRL, now I know what they mean. By the time it's published in one of their handbooks or compendiums, they have fully tested it as much as they could practical. And it does meet up to whatever the authors claim. So, we've done a lot of articles on these. We did a March 2007 on a roll-up. Our latest one was 2017 on how to tri-band it. So those are other talks that we can give on how to tri-band it. I have another talk on how to get gain, a real gain out of a Jpole. It's not as simple as one thinks. So here, it's a slide where the right-hand side is one of the original articles we published in QST. And see, we say uses a single feed line and you can build it for less than $10. That's 20 years ago. You probably put together this antenna now for about 20 bucks. And then you could buy it from us for about 32 bucks. And then, back in 2007, we did a roll-up version of this. And that was from one of my students that mentioned this. He was a ham and he said, hey, you got a really cool antenna, but I go backpacking a lot. Let's see if we can make it into a nice portable roll-up with the same performance. Turned out to be pretty successful. You can use it for emergency communications, plus you could use it for backpacking. Same performance as long as you can erect it. So that was an article. Then our latest article was this one here. This is on a tri-band. And we have a separate talk on that. How do you make from a single band to a dual band? We'll go through that today. And hey, can you add 220 to it? Make a tri-band. We thought about it a lot and we had a good incentive from FEMA. FEMA said, hey, if you can make one of these with no radios, really reasonable performance, we'll buy a bunch from you because FEMA, if you guys are involved in FEMA, they use 2 meters, 450 mainly for the voice channels. And then they try to reserve 220 for packets so it doesn't interfere with the voice channels. Because what they found was, as soon as you try transmitting packet on the same band, like on 2 meters FM, it just desensitizes the receiver. If you're transmitting 25 watts, 10 feet away on top of the roof on 2 meters packet, and you're trying to receive some handy-talkie out there 5 miles away on a channel that's maybe a couple hundred kilohertz away, you just overload the receiver, so there's no way. So their standard was to go to 220 for a packet, which is a good idea. I think then you don't get interference, then they don't. But then you need an antenna. And they wanted a simple antenna that could do all 3 bands, and we did it. And this has no radials. It gave them the performance they wanted. At a very reasonable price, about $50, $60, which is better than anything else that's out there. That's a picture of my daughter, KJ6QXM. She's a master's in engineering and mechanical from Boise State, but she was the ham back then. I talked to her on DMR a lot. And then we also had to patent some of this stuff. I don't think that was my first choice. The original DBJ1, we didn't patent. I just didn't think so. I thought we could publish it. People can take it as is, build it at ham clubs or whatever for ham activities. That didn't happen. People started copying it. Little antenna companies start copying it. They start selling it. They start selling it under even my name saying, hey, buy the Ed Fong antenna from us, published in QST. And that's when I thought it drew the line, saying it was my antenna and selling it for a profit. But what really got me disturbed to start patenting it was we started buying all these antennas that people, it was like 3 or 4 people that were making it, and not a single one worked to our standards. They don't realize how much effort it goes into making sure the materials are correct. We special order our PVC. We even special order our RG170 for coax to make sure the velocity factor is correct. So we take it pretty seriously, and it does work very well. Our twin lead that we use in this is not the stuff you would buy or used to buy at Radio Shack or at Walgreens or whatever. All special made, heavier duty copy for controlled dielectrics and all this. So when people were making these, they were just buying random Radio Shack twin lead. So we weren't happy with it. And so I started, or well, our patent attorney said, then you got to start patenting this stuff if you want your rights to it. So we did patent the tri-band. We patent the gain antenna. And sure enough, when you patent it, people don't copy or even try to copy. So that wasn't my first choice, but that happened. So why Jpo? Well, you know what I found is when I grew up, when I was growing up back in the 60s, being a ham in the 70s, I just used ground planes. That's all I knew, ground plane or maybe a dipole. For VHF, mainly a ground plane. And you would build these things out of an SO239 connector, some number 16, number 14 copper lead, solder a center conductor, and then have 4 little radios, and the thing would work fine. You know, you put an SWR meter on it on VHF, you know, and back in the 60s, I was going through the WB6IQN machine, right above where you guys are on the what do they call that? The Berkeley Hills there. And you know, it would hit the repeater fine. And I guess that's all that's really important at that point. But if you really wanted to improve it, it turns out that there's a lot of things you can do to an antenna. A ground plane is easy to build. It's not the highest performance antenna around. And one really wouldn't choose it if you wanted an optimum design today, not as a starting point, maybe 20, 30, 40 years ago, yes. The Jpo has a much more ideal half-wave radiation pattern. Also, the Jpo, it's end-fed, and we'll get into this later, but why end-fed is a lot more convenient. Here's an example over at Mount Sutro that you guys would know. Just the fact you probably can look out your window if you can see Sutro, get a pair of binoculars. It's probably overcast, but if you saw that, if you can zoom in like this, one of the towers looks like this. A lot of broadcasts, a lot of two-way radio. There's obviously, that's a broadcast TV antenna on top of there. So I don't know who it belongs to, but that's a broadcast antenna. But there's a bunch of two-way radio antennas here. There's a beam, but look at all these verticals. Just by looking at them, there's not a single one I could see that has radials, which means none of them take a ground plane approach like what we used to do. If you had taken this picture 30, 40 years ago, you would see, I used to go up there. Most antennas were ground plane based. You look at even today, the ground based plane antennas, Diamond, X200, X50, they're all ground plane based. And that's really the professionals have shied away from that. Now we'll get into this in a while. Just over time, you get the improved designs. So most are of a Jpo type design internally. One marked advantage is you technically don't need a lightning arrestor. I think this sold a lot of folks on it. When folks showed them, here's a new design, Jpo. The Jpo design is a DC shorted design. That is, if you took a multimeter across it, the center conductor and the shield, you would read 0 ohms on a multimeter. Now, some folks that are not familiar with RF say, you sent me an antenna that's shorted. How can this work? Well, that's at DC. At AC, obviously, at 146 megahertz and 445, it's 50 ohms. That's an impedance. But at DC, it's a short circuit. A ground plane antenna is an open circuit. In an open circuit, you put an ohm meter across it, it reads infinity. Well, that's kind of bad because during a lightning storm, that means to charge the antenna itself, the lead that's going into your radio, into the front end, is not a DC short. So most of these radios can stand maybe 40 volts, 30, 40 volts. Beyond 30, 40 volts DC, if you put that on the input connector to the radio, you'll burn out the front end or the MOSFET if it isn't protected. In a ground plane antenna or in a dipole, here's a dipole antenna, a very well constructed dipole antenna. Copper, this looks like 1/2 inch copper. There's an insulator there that you can't quite see. center conductor goes up here and the shield goes down here. It's an open circuit. So it's an open circuit. It can hold charge. In other words, if there's a lightning strike here, if it's a direct strike, forget it, right? The whole thing blows up. So we're not concerned about that. But if there's a lightning storm a mile away, millions of volts, boom, millions of volts, you can easily see where this can induce about 40 volts, 0.00001% of that lightning strike can induce 40 volts. And if it does, 40 volts, it goes down your coax up here, in this case, and 40 volts sees your radio and your front end's gone and you got to replace your front end. I've done this. I worked at did volunteer work at the Red Cross. They kept on blowing out front ends constantly because you go on top of the roof, there's a lot of RF there. Similarly to the lightning storm, you induce charge and voltages that you don't want. And when that happens after it exceeds 30, 40 volts, most front ends would just blow up. When I show you the Jpo design, it's only 50 ohms or typically 50 ohms at where you want it to be, 2 meters, 146 megahertz. UHF would be about 445 in that range. It's a DC short. And that means even if you build up charge, well, over time it'll short out, it discharges very quickly. So that's very nice. Back to this, if you look at that, I don't see a single ground. Let's take about 2 years ago. There's not a single ground plane antenna left these days. So people learn pretty fast, if you call it 10, 20 years fast. It's a DC short, saves you a lightning arrestor. But I'll show you some other advantages of why I chose this Jpo design. Here's a conventional dipole, and you look at this dipole. It works, it's half wave. But look, you got to center feed it, and that means you got to center feed it at right angles, and you have to have an arm. The further this is away from this mast or from the building, the more ideal it performs like a dipole. Otherwise, if it's too close to the building or too close to the mast, that building or that mast will act as a reflector. So you would want to push it out. But let me tell you, pushing it out is not that simple mechanically, because a mechanical engineer will tell you this. Let me show you. Here's our antenna. Like what I said, this performs, if it's a vertical half-wave dipole, which this is at 2 meters, it performs best when it's further and further out away from this mast or away from this building. Well, that means you gotta hold it up horizontally. And a mechanical engineer will tell you that the further you push this out, the more torque, or R cross F, is in that node. And over time, with this wind is blowing, it's got weight on it, and all that is solder holding it together. Copper pipes are held together by solder. They're not designed to be moving. If you don't move it, they're fine. But can you imagine over time, the wind blows in the winter up and down, left and right, eventually that joint breaks. And you see this all the time. So you don't do that. Typically for a commercial grade antenna, you just can't do that. It's got to be much stronger. It's got to be welded, not soldered. You notice if something is just vertical that you're holding up, let's say I just hold this up vertically. Well, what's easy to hold up? I can hold it up with one hand because it doesn't have an R cross F torque with it. To try to hold this horizontally is much, much harder, much, much harder. So that's why, although this antenna works well, mechanically it's difficult. And also it's a DC open circuit, so it can induce voltages at a lightning storm, and that's not desirable. So again, the pattern's good, but mechanically it just doesn't fit very good. So I was introduced to this Jpo that we're going to get into today, the single band version at least, and then we'll show you how we transitioned to a dual band. About 30 years ago by Denny Monticelli. You guys, some of you guys know him. He's big over at the Radio Historical Society in Alameda. He's one of the officers there. But he was my boss for a long time over at National Semiconductor. And I looked at this Jpo design again. We'll get into the details. I loved it. It worked well. He gave it one to me, made it out of ribbon twin lead, 300 ohm twin lead. Brought it home. It does work well, and it is noticeable. It does work better than a ground plane. About 1.5 dB better. Not night and day, but 1.5 dBs, 1.5 dBs. And so I thought about it. I like this. It was just in a little ribbon, 300 ohms. But why don't we just stick it in a PVC pipe and make it into a base station antenna? And that's what we did. And I also made it dual band. And to date, we've sold well over 35,000 of these now since 2005 or so. So we've been doing this for 15, 16 years on the side here at UC Santa Cruz. And it's not very difficult. It's not difficult to make, and the parts are pretty inexpensive. So by late 90s, 2000, everything started going dual band HTs, dual band mobiles, and people were asking, hey, we want a good dual band antenna now. Now that UHF, in the Bay Area, you guys are in the Bay Area, hey, even all the UHF repeaters slots are all taken up. Even 220 is all taken up now. That's why we did the 220 antenna. But all these guys a lot of folks had Jpoles, but they were single band. And they would say, can we make something that could work at UHF? What they noticed was the VHF antenna was working, at least SWR-wise. A lot of folks think that an antenna is working if it has low SWR. Not exactly, right? You need a little bit more than that. Just because an antenna has a low SWR, that's necessary, but not sufficient. It turns out that most antennas, or virtually all antennas that we work with, always resonate at their odd harmonics. Meaning, a simple example would be, if you made an antenna, a dipole, just a simple dipole, 100 megahertz, and you put an SWR meter on it, it will also resonate at 300, 500, 700, 900 at odd harmonics. If you take my antenna design class, we can explain that very simply in the Smith chart and the waves and why it works that way. That's for an impedance matching. But in terms of the patterns change quite a bit. And I'll explain this in a while. But what we want to get to now is when you use a VHF antenna, 2 meters, at UHF, it's the third harmonic, right? 150 times 3 is 450. The antenna will resonate. You put a bird watt meter or put your nano VNA on it, you'll see a dip. Again, that's necessary, but not sufficient for a good antenna, because when you start using the antenna, say, hey, wait a moment, something's missing here. It is. You're missing about 6 to 8 dBs. You'll notice the matching's great, but you start using it, weak signals are just gone. They're not even as good as a rubber duck quite often. You'll notice this fairly rapidly that the SWR is low, but the performance is not acceptable. So when people pointed this out to me, and I wasn't as experienced back then, I just said, that's an interesting problem. Let me look into it. I just had never looked into it. I started looking into it. Well, I understand what the problem is, and I'll explain it in a while. But they weren't interested in understanding why. They wanted a solution. They said, can you adapt our Jpole antennas that work at 2 meters just fine, and no complaints at 2 meters, but can you make it equally work well at UHF, which ours presently does not? That is not a difficult problem in itself, but the constraint is these are hams we're talking about. I mean, you guys go to Pacificon. Hey, you guys got to come down to the swap meet too, by the way. We're going to start having the swap meet. I've arranged it. We figured it out. Looks like we're going to start in March at the Sunnyvale Library at City Hall. So I hope to see you there. But anyway, I learned about this in the swap meet. People say, can you make these Jpoles into UHF? And they didn't mean, could I do it? I think you always can do it. You could go out and buy one, go buy a Comet or a Diamond, and you can. They wanted cheap hams, right? They're hams. They wanted the design to be, again, it's got to be simple, reproducible. Let's see, I think in the next page. Oh, no fancy inductors, no fancy capacitors, because that's not reproducible. And let me emphasize, no capacitors, because that's very important in any antenna design at VHF and UHF. I mean, HF, you can probably get away with saying, hey, let's say you want to do a trap dipole, and you need a trap and you need some capacitors, 20, 30 picofarads or whatever to resonate the little coils. Yeah, you can get away with it at HF. But if you guys are RF engineers out there, or have played around with RF, you can't specify a capacitor, or very difficult to specify a capacitor that works, let's say we need a 5 picofarad at 150 megahertz. If you got a ceramic cap that says 10 picofarads at 10 megahertz, it's not going to be 10 picofarads at 150. If you get a good network analyzer, it will not read 10. It'll have some series inductance, it'll have some series resistance with it, and then it'll have some capacitors. If you're lucky, you'll have some capacitance. And then you guys that are RF, you'll be familiar with some capacitors have self-resonance. They'll actually resonate with itself up there. So in general, I can't give you a general rule. In my experience, if you open up an antenna, VHF, UHF, and if it has a capacitor in there, some ceramic thing in parallel with solder in, I could say, in general, that's not a very good design. You've got to design it out, because at those frequencies, capacitors are not reliable enough. Or same goes for commercial inductors, like a real cold inductor. A little bit different if you're 1 turn or 2 turns of the wire. That's making your own inductor. But saying, oh yeah, and you need a so-and-so nanohenry inductor that you can buy from Jpo. Now forget that. That's a bad design. Those are way too lossy, the VHF and UHF. So I had to come up with a design that didn't require capacitors commercially or inductors, because you can't buy them and you can't reproduce them. So I tried all kinds of different things, and we'll get into what they were. So here's where the problem is. When you analyze the problem, not the solution, but just the problem, just understanding the problem. And it's important, right? If you're going to solve a problem, you better understand what the problem is. First thing I did was I simulated the single band J-pole on EasyNet, but you can do this, we have ADS, we have more sophisticated software, but this result's the same. You can use EasyNet, which is free online now, or SimSmith is free. You can look at the pattern, and here it is. A vertical dipole, that's what we have. So vertical dipole in free space, and you leave it in free space just as a relative performance measurement. In free space, if a dipole is sitting right here, this is the sky here, this is the earth, and then this is sea level. This would be equivalently sea level. So you would have a transmitter here and maybe the guy standing here somewhere and measuring the field strength. Well, here's the pattern at the fundamental. But at the third harmonic, we said the third harmonic has a good match. So why does it have low performance? This is why it has low performance. Because the actual pattern, again, this is the sky, this is the earth, and this is at sea level right here. When you transmit, most of the RF goes right at 45 degrees, right up into the sky. See, at the fundamental, it's a figure 8 pattern. So if you're looking at the top, it's like a donut, 360 degrees. You're looking at the side, or call it the elevation angle. It covers like a figure 8, the max strength being right at sea level. That's exactly what you want. That's the peak. But again, the third harmonic, about 75% of it goes up into these lobes or goes in the air. So all you're left with is smaller lobe, which is only about 25% of the RF energy. That's the purpose of this talk. I want to get rid of this. Can you make a single antenna which looks like this pattern, both at the fundamental and at the third harmonic, which is UHF in our case? So the first thing you got to learn is the Smith chart. I'm not going to explain the whole Smith chart to you. Take our class. We spend weeks on the Smith chart because it's a concept that RF engineers or high-speed I/O folks really need to know back and forth if you want good performance out of your cell site or out of your interface, high-speed interface between point A and point B. Matching on a Smith chart is very important. But we're not going to go through all of it. All you have to understand in this talk is, here's a Smith chart. It represents half wave, all the way around, half wave, and a quarter wave halfway around. So from here to here, it's a quarter wave. From there to there, it's a quarter wave. So what do you really have to know in order to understand this talk? If you guys can see this, that is a quarter wave stub at UHF. It's about 4.5 inches or so. 4.5 inches, it's not 6 inches because it is in coax, which has a velocity factor, so it's a little shorter. If it were in air, it would be 5 or 6 inches. It's actually, this is about 4.5 because this is our G58. That's a quarter wave stub. But what does the Smith chart tell you about a quarter wave stub? It says, if I short one end, if I put a short circuit, solder the center conductor and shield together, that's DC short circuit. If I move one quarter wave, and for example, at UHF, it would be about 4.5 inches here. So if I short one end, and if I move to here, and I put a network analyzer and measure that, what would it read? Well, most folks would say it will read 0 ohms. You shorted it here. Well, that's where I come in as an RF engineer. I said, no, that's not true. If you understand how waves work and you understand Maxwell's equation, if you short it here at a quarter wave, in this case, 445 megahertz, about 5 inches, it's an open circuit. It might not be infinity, but high. It would reach several thousands of ohms. And similarly, if I leave this as an open circuit, if this is an open circuit at 445 megahertz, what is this? Most people say, well, an open circuit. No, it's a short circuit. It's an absolute short circuit. So it's hard to believe, but that's what the Smith chart says. And we have to take advantage of that. I take advantage of that principle all the time to try to get through with my design. So that's what the Smith chart says. Okay, so here is the basic Jpo antenna. that I had years ago. Twin lead. This is just standard 300 ohm twin lead. Now we do, the ones you buy from us are all custom twin lead with a dielectric controlled, with the conductors a little thicker, number 16 as opposed to like a number 20. So it's not the old stuff you would buy at Radio Shack or Walgreens. It's specially made for us with a low loss dielectric, but the principles are the same. So here we have the dipole. This is dimensions for VHF 2 meters. So it's between 37 to 38 inches, depending where you want the center band to be. So 37.25 is just a number there between 36 and 38 or so. So if you were to center feed this, like that one, it would work. You can center feed, split the wire, have the center conductor go to the top, have the shield go to the bottom. Now this is just a floating piece left over from the twin lead, but because we cut the notch there. But then you would have a standard dipole, and you would have all the problems I was explaining to you before, the torque holding it up. You need some kind of a mass. It'll work, but it's kind of mechanically much more difficult. So in a Jpole, what they do is we just have this half wave piece. So all you need is this piece right here. That piece is just from the twin lead that you cut away. So how do you feed it? You're not going to feed it in the middle. We just explained to you why that wasn't admirable. But what you could say is this is high impedance, low impedance in the middle, but high impedance at the end. How high? In the thousands of ohms. It's not infinity. At RF, nothing's infinity, but it's really high in the thousands of ohms. You need to find some technique where your 50 ohm coax, 50 ohms, which is not infinity, you have to find an impedance transform. You transfer this to thousands of ohms. Because if you could, then that's the feed point right there. Because I said that's thousands of ohms. If I can meet it with the thousands of ohms, it will match. So how do you do that? Back to the Smith chart again. A quarter wave piece of twin lead, quarter wave is about 18, 19 inches. And you say, but Ed, that's 15.25 plus 1.25, that's 16.5 inches. That's not 18. That's because, again, it takes students sometimes to get used to this, the velocity factor. And the way you remember it is, why do you have this? You say it should be 18. I say in real life, it's about 16.25. Why? It comes from a very simple formula. It's so simple, I don't even write it down. It's the speed of light is equal to frequency times wavelength. The speed of light is equal to frequency times wavelength. Or if you look it up in your AWL handbook or your exam, your amateur radio exam book, C is equal to F lambda. You quite often see like that. C equals F lambda. C is the speed of light equals to frequency times the wavelength. The reason why this is only 16.25 is if you use C equals F lambda, you use C as the speed of light, which is 3 times 10 to the 8th meters a second, the lambda at a quarter wave will be 18 inches. But if it's in a material like twin lead, plastic, whatever, it doesn't take you much convincing that. If I've asked you, is it going to be faster than the speed of light or slower than the speed of light in the twin lead material? I think all of you say, well, it's going to slow it down. Nothing can go faster than the speed of light. So what it is this plastic or whatever you have a dielectric has what's called a velocity factor, sometimes abbreviated VF. It's 1 for the speed of light. Any other material's got to be lower than 1. So if it's like 0.8, if we say the velocity factor of this twin lead is 0.8, it means it travels at 0.8 or 80% of the speed of light. So when C is equal to F lambda, you don't substitute 3 times 10 to the 8th meters a second, which is the speed of light. You substitute 0.8 of that. So it's 0.8 times 3 times 10 to the 8th. And then the frequency doesn't change. C is equal to F lambda. But obviously then the wavelength must change. In other words, the physical length of that quarter wave piece will change. Since C is smaller, F stays the same, lambda must go drop also. So for the case of 2 meters on twin lead, instead of about 18, 19 inches, it comes out to about 16.5 inches for a quarter wave. So we short one side, you splice one end together, you short it. And if I convince you from that Smith chart I just showed you, if you go up 1/4 wavelength, in which this case it's 16.5 inches, it should be a very high impedance. Like what I said, it may not be infinity, but it's in the several thousands of ohms. So it matches the end of the dipole, because the end of a dipole is also several thousand ohms. That's how a dipole radiates. Low impedance here, high current. It's high current, low impedance in the middle. In the end, it's low current, high voltage, which means it's high impedance. That's how the antenna works. That's how it radiates. But if you want to end feed it, you got to match that. That's what this will do. This quarter wave stuff will match that. It'll convert this 50 ohms. So where's 50 ohms? Well, this is a short circuit, which is 0 ohms. And this is, the thousands of ohms. You have to find 50 ohms somewhere. It's going to be, the 50 ohms is certainly going to be closer to a short than an open. So originally, I mean, you can simulate this, but originally that's how they found it empirically. Tap it somewhere here, you go measure, you tap it here, tap it there. Eventually by trial and error, say, 50 ohms is right about 1 1/4 inches, 1 to 1 1/4 inches. Sure enough, it works. That's how you tap it. So the 50 ohms comes here because that's 50 ohms right here, because this is a short and that's a high impedance. Turns out about a 1 1/4 inch, you get about 50 ohms. And it kind of makes sense, right? 50 ohms is closer to a short than it is to 3,000 to 4,000 ohms. I'm sure you can simulate this, but usually we just do it by trial and error and you can find that spot. So a lot of folks have taken this principle and really excelled with it, and I'll show you some. One is here, you may have seen this. It's called a copper J-pole, and you can certainly find directions for it on the internet on how to build one. Same principles. There's the half wave radiator. You don't center feed it. Remember, the other one we center fed, and mechanically it's just difficult. You make a transmission line, quarter wave. You make this transmission line out of a T, right? The T's right there, an elbow, right angle, and then you stick it up. And here's your transmission line. Here's the transmission line. Here's the short circuit. Here's the quarter wave. Now, again, that works okay for 2 meters because a quarter wave of 2 meters is about 18 inches. And when you get this T and this elbow and you connect it, unfortunately, that's about 1 3/4, a little under 2 inches. Does it work this way? I mean, you're stretching it, right? You're no doubt pushing the limits. This should be a transmission line, and you're saying, does this act like a transmission line at VHF? And the general rule is it should be 1/10 of a quarter wavelength. In other words, a quarter wavelength at 2 meters, 18 inches, 1/10 of that is 1.8 inch. And that's acceptable, not desirable, but acceptable. And that's what this is, about 1 3/4 inches or so. You're hopping across, it's not good. And this is a little wide for a transmission line at VHF, but it's about 1/10 of the 1/4 wavelength. Sort of acceptable, not optimum, but sort of acceptable. Sort of acceptable that you jump across here to feed it. You have to jump across. Well, you've got about almost 2 inches of exposed wire there. That's not good, starts radiating. And it's even worse, it radiates in a horizontal plane instead of a vertical plane. But all in one, you do this, it works. Yeah, you got these little things that are stretching the limit, but it works. And we've tried them. We experiment with these with my students. We do tests and all that and see whether they work. And this one does work. It works good as a 2 meter antenna. It does not work or hardly works at all as a UHF antenna, because one thing, you lose about 2 inches here in the wrong polarization. It's horizontally polarized. Remember, at UHF, a quarter wave is only about 5 to 6 inches. You can't afford to lose 2 inches horizontal here and think the antenna can work. You lose it, wrong impedance, wrong polarization. So you can't expect that wave to come up here and then start radiating UHF. Again, in an emergency, it's fine. You'll hit a repeater, but for any time you need decent performance, no. But without any tests, we can tell that this is not a UHF antenna. But at VHF, again, we tested these. You would think that it would be marginal by design. No, it actually works. It works quite well. It doesn't match up to ours because we're more optimum. But if push comes to shove, you can go build this and it will work. Another attempt is by Arrow, and we buy these two. I was curious when I saw this Arrow, probably 15 years ago. We bought it and analyzed it. It does make a pretty good, I've never met the engineers there, but it does make a good attempt to solve this problem of the VHF resonating at UHF and having 75% of its signal go up in the sky. So what they do is they parallel two antennas. They have a UHF J-pole, which is 6.5 inches and 19 1/4. They parallel with the VHF one, and they put it through one feed point, one SL239. Kind of a tough way to do it, but they get the match. This thing does work. The problem is this: the UHF signal, it sees a low impedance at the proper antenna, which is 6.5 inch, and this 19 1/4 inch. So that's the proper UHF antenna. But since it's only one feed point, the 2 meter antenna still has a low impedance at UHF because it's its third harmonic. So what happens here? So without the math, the conclusion is in this antenna at VHF, you're fine. a little wide, but it's not measurable. It works fine. At UHF, you've got half your power going into the right antenna, which is this one, but the remaining 50% of your power goes into the wrong one here. It goes into the VHF antenna. Remember, in the VHF antenna, that portion that goes in, you lose 75% of your energy going up into the sky. So that's not good. So this is an improvement. It's not quite there yet. You might ask that pattern, intuitively, why do you get this pattern? Actually, it's a pretty simple explanation without the math. At UHF, what happens is at VHF, it's a quarter wave, and we know that works fine. What's happening in the matching section at UHF? Well, at UHF, we never said this problem had a matching problem. It had a performance problem. What you see is the UHF signal still starts out as short circuit, still 0, but it goes through a half wavelength right here, and another quarter will get it right at the peak. See, at VHF, it's a quarter wavelength that gets it at the peak or the high impedance point. At UHF, it's 3.5 wavelengths. It's, well, I would call it 1/4 and 1/2, 3/4 of a wavelength up, and it gets to the high impedance point again. It's just that it eats up a half a wavelength there, but it matches. It matches because it eats up an extra half wavelength. So that's great. It matches, which means your UHF signal feeds into this line. So at VHF, it goes in here. It's aha. I also see a high impedance point. I'm going to jump right across because I have a good match. Well, what it really wants to see is not at UHF, not at 37.25 inches. It wants to see about 11 to 12 inches for half wave, but it doesn't see that. It sees 37.25. What happens to the current? It goes through here. We'd love to see a termination at 11 or 12 inches. It'll be a half wave, but it doesn't. It continues. It's that continuing current going up the remaining part that now creates a wave that pulls the waveform up because the currents have continued. That's why you get this pattern of the continuing currents going up. The lobes start pushing up into the sky, and that's not what you want. You want it to stop at 12 inches for UHF. Oh, here's another one. Here's a Slim Jim. They try to attempt the twin lead antenna that I just showed you by shorting it. Some people say, oh, it gives you all this gain. It does not give gain. I just want to mention it's just basic Jpo. It doesn't do much to the antenna. Larry Seebeck, who's passed away, has a whole site devoted to the same. Don't believe everything you hear. So how did we make this dual band? Here's the trick. Remember, no capacitors, no fancy inductors, and it had to be doable by an average individual. So we go back to this idea that a quarter wave is a short circuit, a quarter wave stub, which I have here. If you short it at the top, at 1/4 wavelength, it will be an open circuit. And in quarter wave at UHF or RG174 is about 4.25 inches. It wouldn't be 5 because the dielectric slows it down. And so you'll find it's about 4.25 inches is a quarter wavelength at 445 megahertz. So what it says is if I drive this at 445 megahertz, it matches fine, goes through a half wave, another quarter, good match, goes up here. But the good thing is when it comes here, the half wave, 11.25 inches, it sees a high impedance because that stub, the wave stops, you get your radiation, high impedance, the current does not continue, you don't get those lobes. I'm sure it continues a little bit, but it's a very small part of it. If you do that, you'll find that the antenna works well at UHF. And of course, at VHF, that stub means nothing, and we'll show you later how much it means. It really means very, very little in terms of the resonating circuits. At VHF, it sees this whole section as the half wave point, half wave. And therefore, at VHF, it sees this whole thing, and at UHF, it sees only this part. So therefore, you get the nice donut pattern for both frequencies, but with a single antenna. And then this is just an implementation of it, the roll-up version. You can manage to put it all in one piece. We did. One of my students did that. So but one thing you'll notice is here's the roll-up, where we want to roll it all up and put it in a backpack, as opposed to this one is designed to go into a PVC pipe that I just showed you as a base station. The only difference is that the dimensions are a little bit different because these parts here, these parts and these parts here are actually exposed to air as opposed to being in the PVC pipe. So what you'll notice that we call the DBJ2 the roll-up version that operates in air, and we call the DBJ1 the base station one. What you'll notice is if you order both, that the DBJ2 is about 2 inches longer because it operates in air. It doesn't have something to slow down the speed of light. So it's 2 inches shorter if you get the base version because it goes into the PVC pipe. And in fact, it has to go into a very specific PVC pipe because, again, what's called the velocity factor. We like to use Lowell's 23990. That's what we designed to. And it's available. We didn't want to use some exotic material that people can't get a hold of it. So the Lowell's 23990 used to be cheap, but with COVID, the thing's gone up to $6 for 10 feet now. Ridiculous. We used to pick this up for $1.69. But yeah, I just checked the price of my favorite ice cream today and it doubled. So I was shocked. In the end, what you want to see is, so does the concept work? By putting that quarter wave decoupling stub, does it work? According to our measurements, it works. And it works exactly what one would predict. Here it is, a standard 2-meter Jpo at UHF. It's a relative measurement at about 50 yards in a parking lot. When we replace it with our Jpo in the same location, sure enough, you get back to 6 dB. It comes right back. That loss that went up in the sky comes back. And if you look at the actual numbers, and why do we have these exact numbers? Because we try to get these numbers by exactly what the National Bureau of Standards or Institute of Standards and Measurements tells us how to measure an antenna. And typically it's like this. If you want to measure the performance of an antenna on Earth and publish the specs, you've got to measure it on a rainy day, on an overcast foggy day, and then on a sunny day. Each day taking at least 5 measurements and then taking the average of all of them. So that's what this is. These are 15 measurements taken in 3 different conditions. So what we have is, as a reference, mobile quarter wave minus 24.7 dB, and this is just in the parking lot. It's about 50 yards apart. Nothing real fancy, but the equipment. The equipment is Agilent equipment. That's fancy stuff. You replace it with a rubber duct, you lose about 6 dB. That's what you would expect. So try not to use a rubber duct if you want good performance at VHF. Our standard Jpo, a little bit better than a ground plane, than a quarter wave ground plane. In fact, about 1.5 dB better, which is what we expect. And our Jpo is like a standard Jpo, except missing about 0.1 dB. 0.1 dB is negligible, but you do lose about 0.1. That's because of the stub we're using. It will lose a little bit, but 0.1 dB is virtually negligible. Now the proof is in the pudding. Let's go to the next table here. So VHF, it works fine. Our antenna right here, the dual band Jpo. But how about at UHF? Well, UHF propagation isn't quite as good. Same condition, couple of watts, minus 38.8 dB on our spectrum analyzer, about same 50 yards away. A UHF rubber duct loses a few dBs. That's what you'd expect. Sometimes, if it's done properly, you will lose no dB. The reason why is, rubber duct's already 5 or 6 inches, so pretty close to quarter wave. It depends a lot on your handy talkie, your ground, your hand losses, and things like that. But it's pretty good. Standard Jpo, a VHF Jpo, standard VHF Jpo at UHF. That's the thing we're trying to cure. We're saying when you use a VHF antenna on UHF, it's terrible. It is. It's about 6 dB, over 6 dB of loss, because all your signals going up to the sky, warming the sky. So again, if you're talking to an airplane, that's the antenna to use, because 75% of it goes up in the sky. And then if you put out back our dual band Jpo, it almost comes right back. Minus 38, minus 38.8, minus 38.9, as opposed to minus 45, right? Using UHF, a standard Jpo, VHF, Jpo at UHF, you lose 7 dB, 6 to 7 dBs. Can't afford to do that. Not when you're using a little handy talkie on 2 watts, you wouldn't want to. So the antenna principle does work. So here's how we tested. Back in 2008, we had this lab test setup. Now we have this really cool, brand new 5062. Measurements are the same, a little fancier touch screen, color, and all that stuff. The actual measurements are the same. It's got a USB interface that has a floppy disk. But that's our new one. We have both of them. Surprisingly, 20 years later, after $88,000 that we paid for back then, still works fine, a lot heavier. This one's about $48,000. It's a lot lighter. So we're glad we have that. But the one I teach my students to use, of course, just a nano. Just go get yourself a nano, and for what we do, it's fine. I use this nano more than those instruments. You gotta set those things out, you gotta turn them on. Boy, this nano, unless I'm trying to publish an article or something, come on. Smith chart, I gotta get the lighting on. It's great, 60, $70. It goes up to 1.5 gigs. It calibrates well. It's touch screen color. I hate to admit it. I use that most of the time, only when I need to calibrate something that's really critical. That's the only time I use one of these. I would say that's less than probably 1% of the time, just to calibrate, or if we have to do a report or something like that. So those nanos are really nice. You can't afford not to have one. And then so here's the stub. Remember I was telling you the stub? It's not infinity. It isn't. When you put it in a good network analyzer, it actually is right about there. It's several thousand ohms. It's not infinity, but it works. It's better than nothing. And the stub is pretty stable. Here you were sweeping it, but about 445, it's right there. And then I put my hand around it. Yeah, it changes, but it doesn't change it to resin. Resin stays very stable. So I'm pretty confident these stubs are pretty good. And then at 146 megahertz, the stub looks like it's an open circuit almost, but a real open piece of wire looks like that. So it's a little bit different, but close enough. I mean, right where 146 is fine. So see, here's where I mount it. It's mounted at the bottom. It's not sticking out horizontally, so there's no R cross F or torque. And it's all round. It's all round, so wind blows around it. It's not like a ground plane with radials. So the main disadvantage is it is tall. It's basically 3/4 of a wavelength tall, as opposed to a ground plane antenna. It's only 1/4 of a wavelength with radials. But I think overall, this is a much better design. Note there's no lightning arrester. It just goes right down to my shack. It's a DC short. So here's the roll up. With the roll up, what we include when you buy it from us is the antenna itself. And you can't tell the twin leader, but it's twin lead. We include a 6 feet extension. That's a male female connector. So you can just extend it by connecting it another 6 feet. And you can buy extra 6 feet sections. We include all the adapters. It comes with BNC, but we can adapt to SMA and SMA female. You can also buy extra extension. So we sell this. What do we sell this for? $32. $32. It's a pretty good deal. 32. So is the base, 32. And that's how we raise our funds for our group. That's the end of this talk, but here's some other talks if you like this one. I've given another talk on how you get gain out of a collinear. If you're building a repeater or something, you want a little bit of gain. It's not dual band, but it does give you gain. I'll go through how the theory behind that. And then we have another talk on how you tri-band this. How is it that you can make coils for 220 at 220 megahertz through the antenna we just went through today and still have it work at 2 meters, 220 and 440. Here are some radios. We don't sell these, just that they cover 220 and they're pretty, the tri-band radios. If you're interested in getting the tri-band, buying our tri-band antenna, trying out 220 megahertz, they're pretty inexpensive, $100. The Radio Ditty radios, the Baofeng tri-band. Baofeng is usually dual band. You can buy tri-band one, and you can pick it up for about $35 now. These they're about $100, $110. The other thing we sell is I didn't update the slide. We have the new version of this. This is a handheld shortwave radio that we designed for the government about 5 or 6 years ago. This is the original version. The new version we have now has a built-in lithium-ion battery, rechargeable battery. It's got direct frequency entry, and we put the filters in there. It's got DSP filters for CW. It's got 500 hertz, 1.2, 1.8, 2.2, and then AM. And it's all built in. You guys can purchase that if you like, because we get it pretty inexpensive. Get it off. You can go to CountyCom and they have it. It's like $95, about 10, right? And you got tax and shipping, so it's about $110. I think we can get it for $85. So you can save $25 if you buy it from us, because we did part of the design. So the new one's really neat. I got to update the slide. They just released a new one. It's called a GP7. Why don't we? Oh, here. So we sell these. That's how we raise funds. You can buy the DBJ one, which is the base I just went through. It's $32. We make a commercial version of that too, if you're involved in GMRS, FRS, or a MERS. Same price, just noted. And I'll send Justin a spreadsheet that you guys can each fill out whatever you want. We can make the roll up. It's the same price. Again, we make a ham band one, and we also make a commercial version one. The tri-band one, we make a tri-band antenna that way I can give a talk on. And then we have extra extensions and people like that, with some adapters, and then the radio. So we don't sell this old GP5, we sell the GP7. And the upgrade to that GP7's got direct frequency entry. It looks the same size. Built-in lithium-ion rechargeable battery, and it's got the DSP filters for CW and single sideband. Alrighty, so any questions? Did you take any notes on questions?
I have a question for you.
Yeah, go ahead.
Yes. How are you doing these days?
Oh, good. Oh, yeah, you guys heard about my little heart attack. I was shocked about. You heard of, but the word gets out, doesn't it?
Yes, it does.
Yeah, September. I went up to Boise and I gave a couple of lectures at Boise State. I felt okay, and I thought maybe the elevation, a little hard breathing. Went to the airport, came home, and then 4 days later, I said, I better go to the doctor. I'm just having no pain. I had no pain, just a little hard breathing. I'm in pretty good shape, and I swim, bike, and run and all that. And so I just went to the doctor and said, let's give you a COVID test. Gives me a COVID test. No, it's not COVID. Let's give you an EKG. And yeah, he said, hey, I think it's your heart. Your valves are clogging. So, really quick, put in little stents in there, no anesthesia, and I'm back up and around. I'm watching my diet more, although, I can't, I was pretty strict to my diet. I don't drink, I don't smoke, I don't drink caffeine, I don't drink Cokes. At 67 years old, just the genes start catching up.
I'm glad to hear you're improving.
Anyway, questions about antennas?
Just to note, there wasn't a question about buying the stuff, but it looks like Justin said edsantennas.weebly.com for the antennas, correct?
Yes. You can just email me. From there, you can see more details. Our articles are there you can download. And then I wouldn't buy from there. Why don't you guys do a group buy? It says set $45 and antenna is going to be $32. So the savings of $13 plus the postage. So
nice,
probably,
thank you.
Yeah, $15, $16 you'll save.
I had a question. So you were my first big antenna. It's still outside my window.
Okay.
And I used it handheld for a while to try to track the ISS. And I was successful. But I did find myself kind of dancing around my yard in some fashion to try to get the best signal.
Right.
I now have a Yagi antenna, but
yeah, you need a Yagi to track the ISS, right? The signal's not strong enough.
Yeah, I'm just curious if you have any suggestions for people who want to use the Ed Fong Jpo for, I guess, the wrong purpose for tracking things like an ISS.
My suggestion is don't use it for that purpose.
Okay. Well, I don't anymore, but
hey, I got one of those Arrow antennas are really good. The ones made by Arrow, the dual band ones. It's about little over $100, but you can track it really nicely.
Yeah, that's what I use now, especially at night. You can see it blinking. So
yeah, because the thing's moving really fast.
Yeah,
it's really, really quick. And I've seen have you ever seen the space shuttle go across?
Not the space shuttle, no.
Oh boy, have you guys seen with a pair of binoculars? It looks like it's right out of the magazines. You see this thing flying across. You see the wings. It's really white because the sun's shining on it. And you see the little antennas on it, a good pair of binoculars or telescope. It's amazing. It's just that you only see it for about 20 minutes. It's going across pretty quick, but it's really amazing.
And now you have to go down to Los Angeles to see it.
When it was flying, you did not know.
There's one down in Los Angeles.
Oh, you mean sitting stable, right.
Yeah.
Now you just get. But did you even see the flyover before that got retired? They flew it all around the Bay Area with the 747.
I did not know.
Oh, they flew it right over Moffett. You could see it. They took a couple of flights. I took pictures of it with my camera over my roof. Because before they retired it, they flew it all over the U.S. to show people thank you. That was in 2012. And that was really spectacular. Right over in the backyard, I was taking pictures of it.
It was quite a feat to get it to where it is now too. They had to shut down traffic, remove overhead power lines, a whole.
Oh yeah, that's a big plane. It's an airplane. It's the size of a small commercial jetliner, a small one. But to have that thing up in space is incredible. But I think they flew it over here because so many people worked on it. I didn't work on it, but the tiles were done here, the research on the heat tiles and a lot of communications here. Grumman worked on a lot of the communications equipment. So it was really cool.
And we have NASA Ames down in Moffett Park, and that's been a big supplier of technology and intelligence for the space shuttle.
Oh yeah, oh definitely. That's only 2 miles away from me, from where I live right here. So my daughter did an internship there during the summer. Any questions? Any other questions?
Yeah, I got a question.
Sure.
Oh, go ahead, Dick.
Thank you, Chris. Sure. Ed, are your antennas cut for the FM band, or do you have one for single sideband? And
so stock, we cut them for 146 right in the middle. You can cut them yourself. You read our article. If you want a special request, just email me and then we'll label them. We send it to you. If you want to cut to 144 for single sideband, sure, we can do it. It's not a problem. It's just a simple tune. If you read our articles, it's a very simple tune to do.
Thank you.
It's just that we have to do it before, because by the time we set, it's one of these things, you measure twice, cut once. Once you cut it to 146, you can't go back down. No, you can't. You can add to it. Yeah, you could. UHF, you cannot. VHF, you can add to it. You can add a piece at the end and it'll go back down. But I prefer just tell me ahead of time and then we'll trim it. Okay? And Dick, no, Chris had a question, right?
Yes, thank you very much, Ed. Great presentation.
Well, thanks.
Really good. I really enjoyed it. Just a question about 220. Have you ever made a mono bander for that a particular band? And if you have, can you speak a little bit maybe on the performance of a mono bander versus, say, using a tri-bander for 220?
Okay. So we do make a 220 band. We have them in stock. I don't sell that many, but we have them in stock.
I know.
Got it right here, Chris.
Oh,
what is that? That's a 220.
That's your 220.
220. Okay.
Yeah.
Yeah. That goes into
With an end
PVC
type.
pipe, right?
Yep.
With an end connector. Yeah. You know why we don't sell many? Most people say, if I'm going to waste a coax going up the roof, give me the tri-bander.
yeah, I hear you. And I do, I have a tri-bander, not yours, I must confess, but I will say this, that I was just kind of curious. Do you think the mono bander, though, as far as performance, if there's any advantage to that?
Yeah, there is one. We measured it. Yeah, if you look at my talk, the pattern is okay. You know what we lose? We lose bandwidth.
Aha.
The reason why is we lose bandwidth, we get resonance with the coils, but because it's coiled, the Q goes up and we do lose bandwidth. The 221 that Justin just showed you, that has really good bandwidth. It'll cover the entire 220 with no problem. But if you do a coil like what we do in the tri-band, yeah, you can tell.
It's a little narrower.
Yeah, it's acceptable, but it's definitely narrower. I mean, thank God that they cut the 220 band in half 20 years ago. If I had to cover 220 to 225, that would be very hard. Yeah.
Yeah, thank you very much.
But I think most folks, they go, well, I'll go to the tri-band because I need to run the coax.
Yeah, exactly.
You waste the coax. But you're talking LMR 400, that's pretty expensive.
Yes. Thank you.
Speaking of LM400, do you have any preference for the feed line? I have RGA8X feeding. It's about
RGA8X is fine. If you're running,
it's about 38 feet.
Yeah, you're fine. It's okay. At VHF, RGA8X running 30 feet is fine. Even 220 at 440, that's right about the edge. It depends how much performance. You'll start losing about 2 dB. If you looked up in the charts at UHF, about 30 feet, you start losing 2 dB.
Yeah, I can see our repeater from my house, so it's
with LMR 400, you only lose about 30 feet at UHF. You only lose about half a dB. So a dB here and there. Unless you're doing space work. If you lose 3 dB, where the drawing line is 3 dB because that's half. But you lose 1 dB, it's barely noticeable, barely measurable. 1.5 dB, in certain situations you'll recognize. By 3 dB, you'll notice, hey, it's weaker. So yeah, my borderline case is about 1.5. Once you start losing more than 1.5 dB, you can start looking at other alternatives. So RG8X, 30 feet, you're fine. I wouldn't go out and spend $1.50 per foot on LMR 400.
Thank you.
Pretty expensive. And you ever try to work with LMR 400? It's trying to bend garden hose. Right? It's hard. It's not easy to work with.
No, I've never done that.
So because it's solid, a lot of it's solid conductor inside. It's low loss, but it's one step away from hardline. I mean, the turns radius is only about 2 feet. Good times microwave, LMR 400, I use a lot of it. The turns ratio of that is about 2 feet. So you can't bend it. You got to make a slow, it's like conduit. However you can turn conduit is probably the maximum you can turn LMR 400.
I used to be an electrician. I understand that equation.
Yeah,
certainly.
yeah.
But
you can't bend it much, otherwise you get too much loss, or else you'll break the shield in there. So again, long runs like 100 feet or more, you got no other choice. But 30 feet, RG8X is fine. Okay, any more questions?
I had another question.
Sure.
What are you excited about next in ham radio?
What am I excited about next? Well, Winter Field Day is coming up.
We're going to have an event, so
You're gonna
maybe we'll try to make
participate in that?
contact.
Yeah, I'll participate in it. Are you mean technology-wise?
Yeah, I mean, there's digital modes, there's DMR, there's
I do
VHF,
DMR. I do
UHF.
DMR because I don't get on the air very often. I mean, I'm on the boards of a lot of the radio clubs, and I'll get on the nets. But well, I think a lot of these. I've been looking at a lot of these cute little cheap QRP single sideband radios. Starting with the Zygu X90, $500. But have you seen some of these other ones for like $150? They're small from China.
Yeah, they're like copies of ones that people have made here.
Yeah, right.
And then they'll steal it,
But they're pretty good. Oh,
Yeah.
Radio Diddy does a lot of their own designs. They're pretty smart people. I think a breakthrough is in instrumentation. Like what I'm really excited. Do you have one of these spectrum analyzers, the tiny SA? You have one of those?
No.
A tiny SA? Oh, you got to get a tiny SA.
I'm going to search this.
Hang on, I'll get you one. I'll show you. Hang on, I got one in the room.
I'm learning more so I can spend less money.
Let me know when that happens.
Hey, have you seen? So have you guys haven't seen one of these yet? Okay, let me show.
No.
It goes up to 1.5. No, this one goes up to 900 megahertz. Here's the display. Uses SMA connectors.
And that's for audio spectrum? Or
No, up to 1 gig.
Oh, wow.
It's great for troubleshooting noise in your ear. It's fully portable. It's got a NiCad battery with it.
So it's DC to 1 gig.
DC to 1 gig, yeah.
That's
Pretty,
cool.
pretty decent. Plus, it's got USB, so you can interface. They got the software. You can interface it with your computer.
Same form factor as the Nano.
Yes, that's correct. That runs about $60, $70. See, what you guys got to do is what's in Hammer. You got to come to some of our meetings. Once we can't have one live this month because of COVID, but we give away these as raffle prizes.
Is that the Bayonet?
The Bayonet, what?
No, is that the club that you
Oh,
were
no,
talking about?
no, not Bayonet. FARS, Foothill Amateur Radio Club.
Oh, okay.
Foothill Amateur, and then also what's called the Cathay Amateur Radio Club, and then Ceres, Sunnyvale Amateur Radio Club. We give away really good, cool prizes. We give away the quad band, those radios, quad band radios I just showed you, and in the banquet, the last time we had a banquet, which was 2 years ago, we gave away an ICOM IC 7300.
Yeah, we should probably come.
But it's not under our control. COVID is killing us.
So in line with Greg's question there, actually, it's a great question, Greg. What is your favorite mode if you were to operate, or when you operate?
Oh, me?
Yeah. What's your favorite
Oh
mode?
no, I what I basically do is I just do single sideband. Well, I do the nets, on DMR and all that stuff, but aside from that, can I do CW? Yeah, I was a Mars operator CW, but only for contesting. I remember the extra class with the CW. But I'll say before I go to bed at night, 12:30, 1 o'clock, 40 meters, all the Japanese nets, the Australians come in. It doesn't take that much time. I just listen in and see what bands are open. And I've got enough gear. I got Collins stuff, Drake stuff. I got Yesus equipment at home. But like FT8, I don't know, just personally, to me, if it was for my job, I would do it. But you just kind of let your computer do the talking, and then you come back. But I like a lot of old traditional hams. I like to swing your beam to Australia and Japan at night before you go to bed. Can I hear them?
You have an antenna farm at your house?
I did. I still do. I used to have a bigger one, but over the years, I gave away my A3S beam in the ham 4 rotor. So I'm using HF now. It's a fanded dipole on each band, and then later I have a bunch of VHF UHF antennas because that's what I do for a living. But yeah, if you drove by my house, you probably wouldn't miss it. That's what most people say. Oh, you don't have to give me the address, give me the street. And but there's actually 2 other hams within a block of me.
Yep. Look for the porcupines, right?
Yeah, look
They
for the
identify
porcupines. Yes, that's right. That's right. So what do you have, a studio over there, Justin?
I happen to have a studio mic that's not working, but
Oh, what kind of mic is that?
this is a AKG Perception 220.
Oh, wow. Well, that's pretty.
I work for a TV station down that way, so yes.
Oh, which one
I
did you work
download
for?
Create TV, the San Jose public access station.
Oh, okay. Well, you still do? You still come down here?
Oh yeah,
You drive all the way down here?
yeah.
How often?
Now once a week,
Okay.
but we're building our new facility, so
Wow, that's that's an hour and a half for you, at least, right?
it's an hour.
Hour? You can do it in an hour? Okay. Wow.
And
Okay.
you leave at the right time.
So actually, if your club wants to buy antennas, what you could do is you could just pick them up here. Yeah, this would save on the postage. Yeah.
Absolutely.
Yeah,
So we'll work on doing a big club buy.
Yeah,
If
yeah,
anybody
work on
wants
some,
to
yeah.
buy one.
You get a
and
good
we'll make it
discount.
happen. I'll pick 'em
Again,
up.
it's about $15 off per antenna. That's quite
Nice.
a bit. That really adds up.
Yeah, it is.
Any more questions on antennas?
All right. Well, let's give Ed a big round of applause. And thank
Thanks
you
a lot
so
for
much.
having me. Next time I could talk about the tri-band or a gain antenna, or as Justin was just desperate for a speaker, give me a call.
No,
Well,
I
thank-
want to learn about the collinear setup. That sounds phenomenal.
Yeah, thank you very much, Ed. That's
Yeah,
great.
oh, you're
great
very
talk.
welcome. You guys
Thank
have a
you.
good
And-
evening, and Greg there, and hopefully we'll have PacificCon. You know, I didn't go to PacificCon this year. I paid, but then COVID was just too high for me.
Yeah.
I heard the good news. You know, the good news is the payment of tickets was 92%, which is pretty high. The actual attendance was like 40%, which means that's what's important, right? They got the money. They didn't
Yeah.
have the traffic.
I did spend one afternoon there, very protected, but I did spend, oh, it's my first one. I've only been a ham for 2 years, a little over
Oh,
2
okay.
years now. So,
Okay.
but it was very impressive and I learned a lot. Very good.
Yeah. So normally what they told me is the actual attendance was about 40% of normal.
Yeah, it looked pretty sparse.
Yeah.
It did look.
But again, the good news, I paid for a booth and I paid off my tickets, and they said, "You want your refund?" I said, "No, just give it to the club. You guys are hard enough times, setting up something like this and getting, 40% of the people to attend. I mean, that would be upsetting to me. So I said, "Come to keep it." But hopefully by next year it changes. But who knows? It's not under our control, unfortunately. So we'll see. Okay, hey, thanks a lot for having me. Invite me back next time and buy an antenna to help us out. Okay,
Thank
I'm gonna
you.
leave you. Hey, take care.
Thank
Send me
you.
some- Yep,
Thanks, Ed.
Thank
Really
you,
appreciate
Ed.
it.
you're
Be
very
well.
welcome.
Stay healthy.